good evening. So, welcome to the NMTC classes. So, today we will discuss some problems from algebra and number theory. So, here is the first question. You are supposed to find out the number of 3-digit numbers which have odd number of factors. So numbers like say 125, something like that. Okay. So you find out those numbers having 3 digits which have odd number of factors. So the numbers lie between 100 and 1000. It can be starting from 100 to 999. Okay. So it's a counting problem. So what we try to do is we characterize those numbers which are that property. Okay. So the number of the 3-digit numbers having the property that they have odd number of factors. Okay. So we are going to characterize such numbers, then try to count them. Okay. So what you can say about the property of those numbers? So let us look at that. So suppose you take n, any number. You know that any number can be written as product of prime powers. Like for example, we can write it as p1 power alpha 1, p2 power alpha 2, and so on, pn power alpha n. So you know this. This is what is called the fundamental theorem of arithmetic. So every natural number can be written as a product of prime powers. Right? For example, 100 you can write it as say basically you can write 25 into 4 and 5 square into 2 square, like this. Okay. 100 can be written as 25 into 4, which is 5 square into 2 square. So here is p1 power alpha 1 into p2 power alpha 2. So p1 equal to 5, p2 equal to 2. Alpha 1 is 2, alpha 2 is 2. So let me now characterize those numbers which have odd number of factors. So how many factors are there for this d, for this n? How many factors are there for n? Say, let's say positive factors, okay, between 1 and itself, between 1 and n. So we are interested in the positive factors of n, including 1 and n. See, for example, in 100, how many factors are available? Yeah. So they are given by the form 5 power a and 2 power b, right? All the factors of 100 are of the form 5 power a into 2 power b, where a varies from, it can be 0, it can be 1, it can be 2, right? B can vary from 0, 1, 2, right? So the possibilities for this A will be 3, for B will be 3. So altogether there will be 9 ways of having this. So the number of divisors, number of positive divisors of 100 will be given by, let's say, d of 100 equal to 9. So in general, for this number n, how many positive divisors are there? So for this, see, you take any divisor of n, it will be like this: p1 power some a1, p2 power a2, like this, pn power an, right? These a1s can vary from 0, 1, 2 up to the highest power, that is alpha 1. So there are how many ways of having a1? It will be alpha 1 plus 1, right? The choice available for a1 will be 0, 1, 2, 3 up to alpha 1, which is alpha 1 plus 1 in number. Similarly for a2 and a3 and so on, we have alpha 2 plus 1 and so on. Alpha n, we have alpha n plus 1. So many choices. So totally how many ways we can have these factors of n? That is given by the product alpha 1 plus 1, alpha 2 plus 1 and so on, alpha n plus 1. So the total number of ways of having the factors will be given by this, which is the required number of factors. So we noted that the number of factors, number of positive factors of n is given by d of n equal to alpha 1 plus 1, alpha 2 plus 1 and so on, alpha n plus 1. So number of divisors is obtained by a closed formula. So using this form, we can characterize a 3-digit number. Not only that, in general, say having say number having odd number of factors. How do you characterize this? So any number having odd number of factors, yeah, what is the observation? Yeah, can you see that it is a square? It should be a square. Why that is so? We can see that easily. See, when this is odd, what happens? When the number of divisors is odd, then all these alpha 1, alpha 2, let us say alpha I, these must be even. Because see, we are requiring that the number of factors is odd. This is odd. Therefore, each di must be even. That means each alpha I, I'm sorry, it's alpha I. So that means in n equal to p1 power alpha 1, etc., pn power alpha n, all these powers are even. So n is a number having even number of prime factors, prime powers. See, like we have something like p1 square, p2 power 4, like this. So that means that n should be a square. So did you follow? Yes. So we have observed that whenever the number of factors is odd, the number should be a square. Yeah. So we have noted that if n has odd number of positive divisors, positive factors, then n must be a square. N must be a square. Therefore, the numbers between 100 and 999 we are interested in, which have odd number of factors. And we have just seen that they should be squares. So namely, you can see the squares starting with 10 square, right? The highest square will be 31 square, right? So this is the least square, this is the highest square. So we can easily now compute 10 square here, 11 square like this, you see that, 12 square up to 31 square. These are all the squares. We are interested in the number of these. So that's clearly given by 22, right? So just see the way we arrived at the answer. Let's look at the question again. Number of 3-digit numbers which have odd number of factors. So basically we characterized numbers which have odd number of factors. We have seen that if it has odd number of factors, it should be a square. So knowing that it is a square will help you to compute the number of such terms, such numbers. So we are simply calculating the squares present between 100 and 999. Okay, so this is the solution. So we just note an important fact here. If n is equal to p1 power alpha 1 etc. pn power alpha n, which is what is called the fundamental theorem of arithmetic. Every natural number can be written as product of prime powers in a unique way. That fact is called the fundamental theorem of arithmetic. Yeah. And then we have proved that the number of positive divisors is given by this formula. So the key point to note is that this formula implies whenever this quantity is odd, all of these ai should be even, so that n becomes a whole square. I hope the point is clear. So we will look at the second problem. Yeah. So the second question goes like this. The positive integers a, b, c are connected by the inequality a square plus b square plus c square plus 3 less than ab plus 3b plus 2c. Find the value of a plus b plus c. Sandra, was it visible? So let's try the next one. First you notice that the ABC are positive integers. They are connected by some inequality. So a hint is that this inequality restricts the values of ABC. They are whole numbers and they are conditioned by some inequality. So accordingly we are going to find out this A plus B plus C. So directly we don't see any information about ABC. So let us try to rewrite this or manipulate this to get some information about ABC. So they are not able to see the writing. So let's see, A square plus B square plus C square plus 3 less than AB plus 3B plus 2C. Shravan, is it visible? Oh, writing is not visible. Oh yeah. See, nothing is visible. Not visible. Okay, so please come to the YouTube channel. CFAL education. Yeah. So as it is not visible, please come to the YouTube channel and you can see the writing. Yeah. There are 2, 3 are written. Yeah. Okay. Yeah. Fine. So. Okay. So. Okay. So A square plus B square plus C square plus 3 less than AB plus 3B plus 2C. Let us try to manipulate this. What we try to do is we rewrite this so that it is very convenient to focus on the possible values of A, B, C, right? So you can shift the right hand to the left hand side, try to factorize, something like that. Because there are squares, you can expect for completing squares, but completing squares is not really doing, because we are not having terms conveniently. Like you can't have some terms like a plus b whole square or a minus b whole square like that. Okay. So we have to manipulate it and try to see some completion of square. Yeah, as direct completing a square is not possible, you have to make some multiplication factor and then try to do that. So a key for completing a square is because of the presence of squares. Okay. So as it is not directly visible, so we have to make some manipulation. Like, see, it is if I take a square plus b square, I don't have some terms like 2ab like this, minus 2ab or plus 2ab. So I am not able to make a completion of square, not able to do that. So we have to see some other way. So what we try to do, we just try to multiply this by 2 both sides. 2a square plus 2b square plus 2c square plus 6 less than 2ab plus 6b plus 4c, right? Let us now focus on looking at these terms and try to group them. Yeah, so we can look at it this way. 2a square plus 2b square minus 2ab plus 2b square is there, plus 2c square is there. Or then we can look for 2b square, 2c square, then we have 6b and 4c, minus 6b minus 4c, then there is a 6 here less than 0. Now does it look better to find out some squares? Oh, we have to manipulate again. We have to see some more factors. See, we are having a square, b square, no problem, we have ab. So we can look for this a square plus b square minus 2ab together, so that there is a square. So the remaining, there is some a square is remaining, b square is remaining. Yeah, so there is 2b square is there, 2b square is present there. Then c square term looks like this. So we look at the c square term, 2c square is there, minus 4c is there. Then we can see plus 6 is there. So we can look for a square for this. So 2c square minus 2c. So we can see it like this. C square minus 2c plus 1 if you have, we get a square. That means you can look for 2 here. Then we can see the remaining, there is actually 4. Okay. So this part can be taken into a square. 2 into c minus 1 square. So what about the remaining terms? So we already accounted a square here. So remaining part you are seeing here, a square plus b square plus 2b square is there present. So this is already accounted here, 2c square is accounted there. 6b we can account. How do we account 6b? Yeah. So 2b square and 6b we can account. See that 2b square and 6b we can make an account, but there are some extra terms needed for that. Yeah, so what is extra term needed for that? So if you write it as 2b square plus 3b square, so we can write 3b square is there, already we have 3b square, so 3b square minus 6b is there. So we can take 3 out, b square minus 2b, right? There is to be some additional terms you have to introduce. So how do we do that? Okay, so let us try. So we are trying to see that this inequality can be brought into terms containing squares. Okay, so that is an idea, we are getting a motivation, so we try to do that. So let me write it again. So let us try to focus on that issue. Yeah. So let us do that. So 2a square plus 2b square plus 2c square plus 6 less than 2ab plus 6b plus 4c. So 2a square plus 2b square plus minus 2ab plus 2c square minus 4c, right? So this is there with here. Okay, so 2c square minus 4c, that is taken here. So minus 6b. Okay, so plus 6 is there, minus 6b less than 0. Yeah. So let us break this again. A square plus b square minus 2ab. So that is a square, a minus b whole square. Okay. Now let us take the one more a square here, that a square remaining. Then let it be as it is. Now you go for b, terms containing b. So there is a b square there, right? Then we are having minus 6b, correct? 6b is okay, because 6b means you are going to introduce something for a completion square. You should bring 9, right? You should bring 9 so that it becomes b minus 3 the square. So a square will be here. But let us cancel this 9. Let us add this 9 to the right hand side. Okay. So we are maintaining that inequality. 9 is added up here. Now let us account for C. Let us look at C. So 2C square minus 4C. So 2C square minus 4C, okay, plus 6 is there already with you, right? So we have to account for some completion of square here. We can look it as 2C square minus 2C plus actually 1 is required for me to get a square, right? So we just introduce that's actually only 2 is taken here. Already there is 6 here, so we take that 2 here, okay. The remaining 4 will write as it is. Good. So this 6 is broken into 2 and 4, and this 9 is an addition thing actually, okay. So all the rest are okay. Now, so this becomes 2 into C minus 1 whole square, that is plus 4, bring it to the right hand side, it becomes 9 minus 4, 5. See the way it is actually looked, okay. So what happened actually, after multiplying this by 2, you multiply this by 2, you got some equation, right? Sorry, inequality. From the inequality you try to identify the whole squares, completing the squares. So we get finally this one. So finally what we got is A minus B the square plus A square plus B minus 3 the square plus 2 into C minus 1 square less than 5. So this is our focus. Yeah, got my point. So we are having some squares less than 5. Some squares 2 into C minus 1 square like this. Now you can tell me, you can think over and tell me what are the possible values of each of these terms. We are having some terms like this, some x square, some y square, some z square like that. The upper bound is 5, it cannot go cross beyond 5. So there are some restrictions. You can now focus on what are the possible values that each term can take. It can be 0, it can be 1, it can be 4. Because they are squares. It can be 0, it can be 1, it can be 4. Not more than that. Right? So each term on the left hand side, on the LHS, on the left hand side, can have values 0, 1 or 4. An important thing is to note that A, B, C are natural numbers. Otherwise this is possible. Yeah. We are not allowing fractional values. So each term on LHS can have values 0, 1, 4. This is an important observation to develop our goal. Okay. So you see that each term on LHS can have only values 0, 1, 4. So let us see now let us see that not all the terms can be non-zero. If all are non-zero, it's not possible. See, suppose it is all non-zero, like 1, 1, 1, 1. It's not possible, right? 1 plus 1 plus 1 plus 2 into 1. So it becomes 1 plus 1, 2, 3, 3 plus 2 equal to 5. So that's not possible. So we note that not all the terms can be non-zero. So we note that not all the terms not all the terms can be non-zero. See the observations, observation 1 and 2. So let us start focusing on what happens if c minus 1 is 0. So let us now deal with cases. Suppose we have seen that not all terms can be non-zero. So at least one of them should be zeros. So let us suppose that c minus 1 is 0. Suppose c minus 1 is 0. What will happen? Let us analyze. So suppose c minus 1 is 0. What happens is that, see, you are getting the inequality a minus b the square plus a square plus b minus 3 the square will be less than 5. Correct? So if c minus 1 is 0, we note that a minus b the square plus a square plus b minus 3 the square should be less than 5. Now suppose a is 0, if a is 0, what happens? Suppose if a is 0, then you get the inequality like this. So we get b square plus b minus 3 the square will be less than 5. See, what I am trying to do is that I want to see some simple inequality in say single variable which we can easily handle with. So I started with assuming c minus 1 0. Suppose I get the first inequality. In that case, suppose a equals 0, we get the next step. But this actually is easy to see because it's a quadratic kind of thing. We can see what are the possible values of b if this is the case. So we expand this and see, we open these brackets, b square plus 9 minus 6b less than 5, which goes to simplify that 2b square minus 6b plus 4 is less than 0, which simplifies to b square minus 3b plus 2 less than 0. So it factorizes to b square, so it factorizes to b minus 1 into b minus 2 less than 0. And this is possible when this is possible, whenever 1 is less than b less than 2, right? You can see that b is greater than 1, this is positive, b is less than 2, is negative, so positive and negative, right? So this is the only case where this inequality works. So between 1 and 2, you cannot have a natural number. B is a natural number, so this is not possible. So having a equals 0, not possible. So if c minus 1 equals 0, a is equal to 0 is not possible. So we note that a can be 1. If a equal to 1, what happens? If a is equal to 1, what happens to the inequality? So we get the inequality like this. So look at the inequality. First c minus 1 is 0, so we have this inequality, right? Now I put a equal to 1, so I am getting the following. That is 1 minus b the square. I am putting that in this star, okay, in star. So 1 minus b square plus 1 plus b minus 3, that is b minus 3 the square. less than 5. Correct? So a is not equal to 0. I am looking for the chance for a equal to 1. If a equal to 1, we are getting this inequality, which simplifies further. 1 plus b square minus 2b plus 1 plus b square plus 9 minus 6b less than 5. So I am putting a equal to 1 in the first inequality. 1 minus b the square plus 1 square plus b minus 3 the square less than 5. I am getting 1 plus b square minus 2b plus 1 plus b square plus 9 minus 6b less than 5. Which, let us see, it simplifies to a quadratic in b. See, in this step also you are getting a quadratic in b. Here also you are getting a quadratic in b. So the quadratic is now 2b square minus 8b plus 1 plus 1 2, 2 plus 9 11 minus 1, sorry minus 5, I'm sorry, 1 plus 1 2, 2 plus 9 11 minus 5. So that is equal to 6 less than 0. 11 minus 5, 6 less than 0. Right? So again this factorizes to something simple, b square minus 4b plus 3 less than 0, and then we can factorize this. So this factorizes into b minus 1 into b minus 3 less than 0, right? And that is possible. B is between 1 and 3. See, so if a equal to 1, I am getting that b has to be between 1 and 3. Just like this case, in the case we are getting 1 less than b less than 2. We are having 1 less than b less than 3. That means b should be equal to 2. Yes, so we are getting b has to be equal to 2. So if I assume that c is equal to 1, a is equal to 1, and I am getting b is equal to 2. So c equal to 1, a equal to 1, and then I am getting b equal to 2. So this is a possible value, 1 plus 1 plus 2. So the answer is 4, we can expect for that. But to rule out the other possibilities, so you should make sure that other possibilities are ruled out. Okay. So let us start with say other cases. So b is equal to 2 is the value we are getting, right? Now suppose we start with a is equal to 2. See, a cannot be 0, a equal to 1. Now we are going for a equal to 2. A equal to 2, again we analyze the inequality again. You have to analyze the inequality star and see that this doesn't give proper solutions. Okay. So that is a case which is impossible. Okay. Now we can look for c minus 1 square equal to, see, we have taken c minus 1 equal to 0. We got this conclusion. Now c minus 1 square equal to 1. See what happens. Like that you have to analyze again and again and completely see that these are the only three possible values. These are the only possible value. C equal to 1, A equal to 1, B equal to 2. So the details are left to you, but I hope you to follow the main argument. So the given inequality of natural numbers, we are going to rewrite this in this form, in a convenient form, to restrict the values of A, B, C. So the basic strategy is to see that this inequality on natural numbers makes ABC restricted, hence a few values of ABC will be there. To identify that, we have to manipulate it in a suitable form. And the motivation for this manipulation is because of the presence of squares, A square, B square, C square, you are trying to get whole squares like A minus B square and so on. And this inequality cannot hold for any values of these terms. It can hold only for 0, 1, 4, and that gives you to restrict the values of ABC. So that is the nice problem on natural numbers. So we go to the next one. So let's look at the next problem. The question is asking the sum of all roots of the equation modulus of 3x minus modulus of 1 minus 2x equal to 2. That s is not there. So we have to find the sum of the roots of the equation. So recall the knowledge about modulus. So it's an important function on set of real numbers. So modulus is defined like this. Mod of x is defined as x for x greater than or equal to 0 and minus x for x less than 0. So what it means is that for x equal to, say for example 1.5, mod x is equal to 1.5 only, and if you take x equal to minus say 3, mod x takes a value minus of minus 3, that is equal to 3. So it always assumes positive values, but it is defined as x whenever x is non-negative and minus x whenever x is negative. So it has two functions on different domains. Okay. For negative values it is taken as y equal to x, and negative values it is defined as y equal to minus x. So basically we have a graph for this which is shown here. For positive values it is y equal to x, a straight line, and for negative values of x it's minus x, straight line like this. So that is the graph of mod x. Okay, coming to the problem, we will simplify the left hand side carefully. How do you simplify the left hand side? So there are some points where the sign changes. For example, if you take mod x, the sign changes at x equal to 0. So suppose you take a function like x minus 1, the sign changes at x equal to 1. That means it is x minus 1 whenever x is greater than or equal to 1, and 1 minus x whenever x is less than 1. Okay. So the sign changes at the point x equal to 1. Correct? The graph of this looks like, again a set of two lines at x equal to 1. The value is 0. So y equal to x minus 1 for positive, x minus 1, right? So it is a graph like this. And 1 minus x a graph like this, right? So at 1 x equal to 1, there is a change in the sign. Okay. So that means now in our question, we have to look at those points where the sign changes, the function formula changes. See, look at the data. 1 minus 2x. So x equal to half is a point here where it changes, and let us see further. So x equal to half, the innermost modulus changes. So what happens if x is positive, x is greater than 1 by 2, then you have 2x minus 2x is greater than 1, 2x minus 1 is greater than 0. So 1 minus 2x will be equal to, see, 1 minus 2x is negative. Therefore, this is negative means the mod of this should be, see, mod of x equal to minus x whenever x is negative. So this quantity is negative, therefore this should be equal to, negative of this, that is equal to, negative of 1 minus 2x, which is equal to 2x minus 1. So in the case x is greater than 1 by 2, we have this conclusion. That means if x is greater than half, I am having the left hand side as mod of 3x minus 2x minus 1, right? That simplifies to mod of 3x minus 2x is x plus 1, and x is already positive, not only positive, it is greater than half, so x plus 1 is also positive, so this should be equal to x plus 1. So we made an analysis to observe that the left hand side is actually equal to x plus 1 for these values. Further, what further observation you can make? Yeah. You see that if x is less than half, what happens? X is less than half, what happens? So you see that 2x minus 1 is negative and 1 minus 2x is positive. Therefore, 1 minus 2x, the given function in the left hand side, will be equal to 1 minus 2x only. That means the left hand side simplifies to that is 3x minus mod of 1 minus 2x, left hand side simplifies to 1 minus 2x, which is equal to 5x minus 1, right? So under this assumption, we are having the left hand side as equal to LHS equal to 5x plus 1, mod of 5x plus 1. So again the sign of this depends on x equal to x is greater than half 1 by 5 or less than 1 by 5. So x equal to 1 by 5 is a point where it changes. So you should look for what happens if x is less than and greater than 1 by 5. So suppose you take x is greater than or equal to 1 by 5, what happens? 5x minus 1 is positive, no negative. So mod of 5x minus 1 will be equal to 5x minus 1. Right? So in fact we can introduce half equal to here. So finally what we got is, if x is lying between 1 by 5 and 1 by 2, we are getting the conclusion that left hand side is equal to 5x minus 1. Correct? Yeah. For these values, more than 1, it is x plus 1. For this range of values, we are getting this second part. Okay, this first part. Okay. Now, this is obtained because of this assumption, right? X is greater than or equal to 1 by 5. So, you have to check what happens if x is less than or equal to 1 by 5. Less than 1 by 5. So, if x is less than 1 by 5, if x is less than 1 by 5, what happens? You notice that this 5x minus 1 is negative. So, the mod of 5x minus 1, that will be 1 minus 5x. Already we understand that x is less than or equal to 1 by 2. Because whenever x is less than 1 by 5, that's also true. So, in the range, here we are getting 1 minus 5x. So, that is the third part. So, we get 3 parts now to the function of LHS. So, the given problem, that is 3x minus 1 minus 2x equal to 2. This given equation simplifies in the following way. On the left hand side is simplified as, this left hand side looks like this. I am writing again 3x minus 1 minus 2x modulus, this is equal to, I am summarizing what we did so far, that is x plus 1 whenever x is greater than or equal to 1 by 2, and 5x plus 5x minus 1 whenever 1 by 5 less than or equal to x less than or equal to 1 by 2, and 1 minus 5x whenever x is less than or equal to 1 by 5. Okay. So, 1 minus 5x whenever x is less than or equal to 1 by 5. Okay. So, 1 minus 5x whenever x is less than or equal to 1 by 5. Okay. So, 1 minus 5x whenever x is less than or equal to 1 by 5. Okay. So, 1 minus 5x whenever x is less than or equal to 1 by 5. Okay. So, 1 minus 5x whenever x is less than or equal to 1 by 5. Okay. So, 1 minus 5x whenever x is less than or equal to 1 by 5. Okay. So, 1 minus 5x whenever x is less than or equal to 1 by 5. Okay. So, 1 minus 5x whenever x is less than or equal to 1 by 5. Okay. So, 1 minus 5x whenever x is less than or equal to 1 by 5. Okay. So, 1 minus 5x whenever x is less than or equal to 1 by 5. Okay. So, 1 minus 5x whenever x is less than or equal to Yeah, at 1 by 5 both are equal to 0, so that's not a problem. We have this following simplification of the function. Yeah. So from this simplification of the left hand side, we should be able to know, compute the question, the sum of all roots of the given equation. So how many x values are there, so that is equal to 2, left hand side equal to 2. So that is possible when x equal to, you can see that from the following, so 3 cases you can observe, 3 formulas. So this is equal to 2 whenever x plus 1 equal to 2, and that is whenever x is greater or equal to 1 by 2. So x is equal to 1 is the possible value of x. Further, I want this to be equal to 2, I should take x to be equal to minus 1 by 5. So these are the possible, these are the roots of the equation. So the given equation in the problem is satisfied whenever x equal to 1 and x equal to minus 1 by 5. Both are in the proper domain. Yeah. So that means, so we cannot take x equal to 1 by 5. Is it possible? So x equal to 1 by 5, that is already, okay, so that is equal to, yeah, so I want it to be equal to 2, so that's only minus 1 by 5, right? 1 minus 1 by 5, not 1 by 5. So these are the two possible values of x. So hence the final answer comes out as, the answer will come out as equal to, that is 5 minus 1 by 5, that is 4 by 5. 1 minus 1 by 5. 1 minus 1 by 5 goes to 4 by 5. So the sum of the roots is given by 4 by 5. So this question is based on the concept of the modulus function. Okay. So you should actually discuss that into different cases. So where the function form changes, you have to identify the values of those points, then accordingly the simplification of the modulus function should be done first, then solve the equation. Fine? Yes. So let us pass to the next problem. Yeah. So the question number 4 is as follows. Let a comma b are such that a plus 1 by a plus 1 by b equal to 1 by a plus b, and a by b the cube plus b by a the cube equal to 2 into square root n. So n is a natural number. What is the value of n? So let us try to simplify the hypothesis. See, we are going to use this hypothesis to evaluate this expression. So how do we use this? So let us simplify first. This 1 by a plus 1 by b equal to 1 by a plus b. So that simplifies to
AB is equal to A plus B whole square.
yeah. So we'll take LCM AB upon, it becomes B plus A, right? Yeah, equal to 1 by A plus B. Correct. So we get A plus B the whole square equal to AB, correct? Yes. Let us simplify this further. So A square plus B square plus 2AB equal to AB. And hence we get A square plus B square plus AB equal to 0. So that is the information we collect from the given hypothesis. The problem is how this is related to the goal. How we can use this hypothesis to the goal. That is the problem. So that is not visible directly. So we can see there is a cube by b cube plus b cube by a cube. So we have to see some simplifications. So let us try. So the given hypothesis is simplified, and we should try to see how this can be used. So a square plus ab plus b square equal to 0. Yeah, it's very troubling. So if I open this immediately, I can't notice anything. A cube by b cube plus b cube by a cube equal to 2 root n. See, if I open the left hand side, how do you use that here? It's a bit question. So you should find some other way.
So just divide by AB and do whole cube by bringing minus 1 here.
Yeah. So what do we do? Divide by
Divide by AB.
Divide by AB. So when you divide by AB, so you have some other way of writing the same hypothesis. So how does it help you? So when you divide by AB, it becomes P cancelled out, A square by AB, A square by AB like this, plus 1 plus B square by AB. Is it like this?
Yes, sir. Do A by B plus B by A is equal to minus 1.
Yeah. So it becomes A by B plus 1 plus B by A equal to 0, right? Yeah.
Yes, sir.
So what
And
does it mean?
bring
Yeah.
-1 on the
Other
right
side.
hand side,
Okay. A by B plus B by A equal to -1. Yeah.
and then whole cube.
Let us try. Yeah. So you mean to proceed like this, right? A by B plus B by A equal to -1. Then trying to cube it both sides. Yeah. Just try it out. So a cube plus b cube can be obtained. So some x cube plus y cube can be obtained, right? Yeah. Is it possible to complete the solution? You know
Yes,
that
sir, by cubing.
x plus y the whole cube equal to x cube plus y cube plus 3xy into x plus y, right? So now we can use this fact so to work out that x cube plus y cube. So that means you can write it like this. So cubing, so what we're having is a by b plus b by a the cube, that will be equal to a cube by b cube plus b cube by a cube plus 3 into 1, right? 3 into 1 plus that x plus y equal to -1, right? Yeah. So a plus b, a by b plus b by a equal to -1. So substituting this, we are going to get the final answer. What is the final answer?
So the final answer is 2.
2.
A cube.
So yeah, that's true. So final answer goes to a cube plus a cube by b cube plus b cube by a cube will be equal to, now it comes out as 2. That is -1 cube here. So here is 3 into -1, so it becomes 3 minus 1, that is equal to 2. So that gives the answer for n. Yeah, so it's nice problems to focus on the algebraic techniques. So with this I think we can stop for today. So we'll continue next class. So thank you very much.